All right, hey folks, in this video we are going to take notes on compound events using theoretical probability. And before we even take any notes here on compound events in math, I wanted to remind you guys that you know what a compound sentence is in English. It's when you have two sentences joined together using the word and. What we mean by that is, like, on its own, Amy's alarm did not go off is a sentence. She was late for school is a sentence. But it is now a compound sentence because we've joined those two with the word and. So Amy's alarm did not go off and she was late for school, period. Okay? So compound is when you have two or more of something, and that's what we mean by compound events here in math, when you have two or more separate events. Now we're going to explore a lot whether or not the events are independent or dependent. And to get us started here, if the outcome of the first event impacts the outcome of the second event, we know we're dealing with dependent events. Something's depending on something else. Now, if what happens with the first event does not impact the second event, then it's independent. They're independent of each other. All right, so here's a couple of examples just to get us started with what we mean by two events. And in the first example here, we're going to be taking a look at these the dice. In math, we just call them a number cube simply because one of them is called a die. And it just looks a little bit weird sometimes to be like a die is rolled. So we just call it a number cube a lot of the time in math. Now you guys know this is going to be really easy. On one of these things right here, the chances of us getting a 3, there's a 1 in 6 chance that we're going to get a 3. Now the chances that we're going to roll a 4 on the other one, there's a 1 out of 6 chance with that. So what we can see here is that there's going to be a 1 out of 36% chance that we'd get a 3 and then a 4. Now I just flipped back over here, you can see to the Google Slides that we did, and you've already seen here that there's 36 total outcomes when rolling two dice. And what we're looking at in our notes is the chances of us rolling a 3 then a 4. And right here in the chart, you can see that's us rolling a 3 on the first one, then a 4 on the next one. So that's the 1 out of 36 for this entire scenario. Now you might be asked to make that a percent, in which case you can just do 1 divided by 36 and be good to go. All right, now for the next one, what are the chances of us rolling a multiple of 3 followed by a prime number? Now before we do anything with this, I wanted to remind you guys that multiples of 3 are things like 3, 6, 9, 12, 15, and so on. So if we're talking about something that's going to be on a number cube, these would be the options. We have 2 out of 6 there. Now the prime numbers, I wanted to remind you guys that one is neither prime nor composite, because to be a prime number, you have to have two factors. 1 and then the number itself. So the only way we can get 2 is to do 1 times 2. So 2, 3, 5, 7, 11, 13, these are prime numbers. Now on one of our number cubes, we have 2, 3, and 5. Okay? So that's where I'm getting the 2 out of the 6 and the 3 out of the 6 right here in my notes. We have 2 multiples of 3 out of 6, and half of them were prime. Now you can multiply 2 times 3 here, y'all, and get 6. And then 6 times 6 is 36. And then you have this to reduce, which would be 1/6. Now personally, I don't like to have to wait to the end to reduce. So what I do is I go ahead and reduce them first before I multiply. 2/6 reduces to a third. Obviously this is a half. And now you've got 1 times 1 and 3 times 2, and it gets you the simplified answer already. So there is a 1 in 6 chance that if we're going to roll these things twice, we'd get a multiple of 3 and a prime number. And if I go back to the Google Slides, again, remember, we're basically saying that 6 out of the 36 would be a multiple of 3 followed by prime. So let's go find them. So a multiple of 3 followed by prime, we're going to have this 3, 2, there's 1. Then it was 3, 3, and then 3, 5. Then we could have had a 6, 2, a 6, 3, and a 6, 5. And those would have been all of the ways we could have gotten a multiple of 3 followed by prime. Now for the last one, you'll notice I've gone ahead and reduced. You know that half of them would be even. The chances of us getting even is half. And a 3 or a 5, that's 2 out of the 6. And so that reduces to a third. So then here when we multiply, we'll get a 1 out of 6. Okay? So when finding the probability of two events occurring, you just take the probability of the first event and then multiply it by the probability of the second event. Now the next part of this video is us going to be exploring whether or not they're independent of each other or dependent on each other. Friendly reminder, if one of them is not impacted by the other, it's independent. And if one of them is impacted by the other, it would be dependent. All right, so let's explore. So if you're going to roll a die and then toss a coin, what happens when you roll this thing has nothing to do with what happens heads or tails when you flip a coin. So these are going to be independent events. What happens here will not impact this one. All right, now let's take a look at answer choice B. Here it says we're going to take a marble out of a bag, and then we're going to take a second marble out of the bag. Now with this one, you might not know yet how to think of it as independent or dependent. So let's look at answer choice D actually, and you'll see that what what problem D shows is that when you take a card from the deck, this one says that you put it back. So you might draw a card from the deck, get whatever you get, and when you put the card back, that means that the next time it's still out of 52 cards, so this is independent. When it tells you that you're putting it back, you are not changing what the circumstances are for the next draw. So now let's go back to B. Since it doesn't say anything about putting it back, let's say that there's 10 marbles in the bag. And when you draw one of the marbles out of the bag, for the next one, there's only going to be 9 marbles left in the bag. So whatever you get on the first one will impact the probability of what you get for the second draw. So this is an example of dependent. When you don't put something back, the second outcome is affected. All right, so now with answer choice C, we're going to choose somebody from a group of 50, and then we choose another person from that same group. So let's say out of 50 people, I've got 30 boys and I've got 20 girls. All right, we've got 30 boys and 20 girls. So if I want to know the probability that I'm going to select a boy, well, the first time it's 30 out of 50. There's 30 boys out of 50 kids. But if I have already picked one person, then the next person that I pick is only out of a group of 49. And then we can see here, if I want to know the probability that I'm going to pick a boy and then another boy, now there's only 29 boys left in the class out of the 49 possibilities. So when your denominator changes like this, that's how you know you're dealing with dependent events. All right? Now let's explore a couple of scenarios where we're going to practice both how to find if they're independent or dependent, and then actually how to calculate them. So for right now, we are on number 2 here. And we've got bag A contains 9 red and 3 green. So I've told you here, bag A has 9 red and 3 green, and here's bag A. 9 red and 3 green marbles. Now bag B has 9 black and 6 orange marbles. So here's the deal with your 2 bags. Now if we're going to select a marble from bag A, and we're going to select a marble from bag B, notice that whatever happens over here, it's a separate bag, so it's not going to impact what happens over here. Now, when you see stuff like this, here's how you read this, y'all. This is saying the probability of green and then the probability of black in the other bag. So the chances of us getting green right here, the probability of green is going to be a 3 out of the 12. You see I've got blanks here where I'm just listing out my events. So this is the green, and now for black over here, the chances of us getting black would be 9 out of these 15. So here's the strategy that I have for these problems. When you're reading through, go ahead and just draw the blank space for your probability, and underneath it, label it what it's for. So this was the probability of green, this was the probability of black. Now, in that setup right there, like I said, those are not reduced, so let's go ahead and reduce them. This reduces to a 4th. This reduces here, both of these are divisible by 3 to 3/5. So when you multiply now, you're going to get 3/20, and 3/20 would be the probability that we select green here and then black here. And you never know if you're going to be asked for it as a percentage or as a fraction. So as a percent here, this would be 15%. You just multiply here to get 100. So times 5, so times 5, so 15%. So we've got it here both as a fraction and a decimal. And in the blank, when it asks us, is this independent or dependent, we're going to put independent because whatever happened from bag A does not impact bag B. Now, before we take a look at the next question about a standard deck of cards, I wanted to review the deck of cards with you guys here in this video. The standard deck of cards has 52 cards in the deck, and you can see that there's 13 of the clubs. We have 13 spades, 13 hearts, and 13 diamonds. So there's 13 of each of them, and there's 4 of each type. So we have 4 aces, 4 twos, 4 threes, and so on. So half the deck is black and half the deck is red. And now let's go back to this question here. So if you draw 2 red cards from a standard deck of 52 without replacement, would that be considered independent or dependent? So because it says without replacement, we're not going to put the card back in, and that automatically makes this dependent if you want to write that right here in the blank. These are going to be dependent. Now, the probability of us selecting a red, let's actually calculate it. There's half the deck is red. We know half the deck is red. And that's going to be then, that would be 26 out of the 52. Now, if you take a red card out, there's only 25 of them left, and there's only 51 cards left in the deck. So you don't have to put 26 over 52. You can go ahead and put a 1/2 here because that reduces. But then for the next one, we've got that it's a 25 out of 51. And when you multiply here, you're going to see that 1 times 25 is 25. And then 2 times 51 is 102. And then let's just get our calculator out real quick to see what that would be as a percent. We've got 25 out of 102. So that's 24.5%, 24.5%. So again, this is dependent because what happens with the first draw will impact the second event. All right. Now for number 4, we have that there is only one government class, and Wes and Maureen are both in that class of 38 students. We want to know the probability that they're both going to get selected, and we want to know if that's going to be independent or dependent. Now, if Maureen is the first one we want to know about, she is 1 out of 38 kids. So there is a 1 in 38 chance that Maureen gets to go on the trip. But Maureen has now been selected, which means there's only 37 kids left in the class for it to be Wes's turn. So now Wes only has a 1 in 37 chance compared to the 1 out of 38. So in this situation, because our denominator changed here, we can see that this is dependent. If you want to put that in the blank, this would be dependent. Now for the numerators, we've got 1 times 1, which is super easy. That's 1. But now for the denominator, I'm going to use my calculator to do the 38 times 37. So 38 times 37 would be 1406. 1406. So you can see that there is a very, 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 very small chance that we'll select Maureen and then we'll select Wes. Now, if you want to back up and think of it this way, though, if you want to say it doesn't matter if we pick Maureen and then Wes, like what if we picked Wes, then Maureen? Basically, then what you're saying is, okay, we want Maureen and Wes, which means those are 2 kids out of the entire 38 class. And when we're like, what are the chances that it's going to be those exact 2 kids picked? You can see here that that would be the answer. So it really depends on how we're thinking about it. In this video, the problem's not particularly clear if it would want this answer or this answer. But because of the way it's set up, where we have Maureen, then Wes, we're going to go with this answer right here, calculating the probability that Maureen gets picked first, then the probability that Wes was picked after. So this is what we're going to go with here. All right, if you guys will flip over now. And you can see how this next problem is a lot similar, like a lot like the one we just did, but here's how it's different. The only difference now is that Wes is in a class of 18 and Maureen is in a class of 20, so they're in separate classes. So the probability of Maureen getting selected, she's 1 out of her class of 20. And now if Wes is in a different class, then he's 1 out of 18 students. And so Maureen's class has nothing to do with Wes's class, and now this is independent events. These are independent. And even though the denominators are different here, it's because it's a totally different class. So now when you multiply here, you've got 1 times 1, and then 20 times 18. And if you just do 18 times 2, that's going to be 36. So just put an extra 0 there, and we've got 1 over 360 for this independent event. All right, now the other thing I wanted to do, let's just compare real quick. Is it more likely if they're in different classes or less likely? So the calculator here, if we do the 1 out of 360, here, when they're in different classes, there is a 0.27%, which is basically a 0.3% chance that both of these kids will get to go on the trip. So if they're in different classes, it's a 0.3%. Now, if we go back and see when they were in the same class, and again, we'll forget about that here. If they're in the same class, the 1 out of 406, obviously, I mean, we don't even need to do the math here because the denominator is so much bigger. We can see that that's even less likely. It's way less likely when they're in the same class. Now, if they're in separate classes, it's a little bit more likely because, again, independent events. All right, if you were to roll a die 1 through 6 and spin a spinner 1 through 4, are these going to be independent or dependent events? So whatever we get when we roll the die is not going to impact whatever we get when we spin the spinner. So these are definitely, definitely, definitely independent of each other. They're independent, okay? Now, if we want to know then what are the chances that I'm going to get a 4 when I roll the die and then a 4 on my spinner, all right, so there's a 1 in 6 chance that this will happen when I'm rolling that number cube. And then if your spinner only has 4 sections and I want to know the probability of getting a 4, now this is 1/4. So when we multiply, we're going to get a 1 in 24 chance of these independent events occurring. There's a 1 in 24 chance that we'd get a 4 and a 4. All right. If you were to select 2 cards from a deck with replacement, meaning you're putting it back into the deck, would the probability of getting an ace and then a king be independent or dependent? Now, because we replaced it, it's independent. So the chances of us getting an ace, there were 4 aces out of 52 cards. And when we put it back, we still have 52 cards in the deck. Now, how many kings are there? There's 4 kings. Now, here's the beauty of this. You guys know, we already said that there's a 13th of them are aces. That reduces to a 13th. And this reduces to a 13th. And we can see that right here. That's one of the 13 sections. And then a king is also one of the 13 sections. Okay? So when you reduce that, now all you've got to worry about is 13 times 13. And so this is going to be a 1 over 169 chance of that occurring. All right, now for practice, I just want you guys to try 8, and then I want you to try 9, and then you'll have a chance to see if you're right. We'll go through those in class. But in the video, I want us to also look at number 10 real quick. So you're going to choose 3 objects at random from all of these objects without putting them back in. So what's the probability that we get a heart, a tree, and an umbrella? So a heart, there's 1 out of 7. But now if we don't put the items back in, then there's only 6 items back in the bag. So then the chances of us getting a tree is now 1 out of the 6 objects remaining. And then if that's been taken out, there's only 5 objects remaining. And so then the umbrella would be the 1 out of the 5. And now we can come through and multiply these and see, whoops, not equal, that should be equals. So this would be a 1 out of, and this is 30 times 7, so this would be 1 over 210. So the denominator in all of these problems is a 210. And then when you do it again, you're going to do A, B, and C again down here. And it asks to do this all over again, but now assuming that you do put the objects back in. So if we took A and assumed we did put the objects back in, let's try it again. So a heart, 1 out of 7 hearts. You put the heart back in, so then there's 7 shapes left, and you have a 1 out of 7 chance of getting the tree. And then there's still 7 shapes, so then you'd have a 1 out of 7 chance for the umbrella. And then here, when you do 7 times 7 times 7, I think it's 243. Let me double check. 7 times 7 times 7. Oh, 343. It's 343. So in this case, down here, your denominator is going to be a 343. and then you have 1 times 1 times 1. All right? So that's going to be the end of this video. Don't forget you've got to do 8 and 9 on your own, and then you're going to try number 10. We'll talk about 8, 9, and 10 in class. You're also going to be doing the other page on your own, but I have a video to support with that in case you feel like the questions are too tough. All right? Thank you.